All right, guys, today we are going to go over molarity. Molarity is just a fancy name for concentration. Concentration is going to be measured with the unit of molarity, and we abbreviate molarity with a capital M. There are two important terms that we need to know when we're talking about concentration. The first is solvent. The solvent is the substance that is doing the dissolving. The solute is the substance that is being dissolved. Together, these two components make up a solution. So, a solution is something that you're familiar with, that you use all the time. A great example of this is Kool-Aid. If you've ever made Kool-Aid from a powder mix, that is actually a great example of a solution. So, if we are talking about Kool-Aid, there are two parts to it. There's the water, and there is the mix, or the powder. If we were classifying these as solvents or solutes, we would see that the water would be our solvent, the thing that is doing the dissolving, and the powdered mix would be the solute, the thing that is being dissolved. Those two parts are both critical in a solution. Let's look at two examples of a solution. I have it drawn here. Notice that in each beaker, I have two components. I have the liquid that is doing the dissolving, or the solvent, and I have the dots which represent the dissolved solute. Notice that both of my containers have the same volume. They both contain 1 liter. But my first container here has a lot more dots. The more dots we have, the more concentrated the solution is. If you think of concentration, or that term in your everyday life, if something is concentrated, that means that there's a lot of things confined to a small space. Same is true here. We would refer to this as a concentrated solution. This beaker over here does not have as many particles dissolved in the solution, and we would refer to that as a dilute solution. If you think in terms of your Kool-Aid, concentrated and dilute would equate to how sugary or sweet your Kool-Aid tastes. If you said you had a concentrated solution, this means that you'd have a lot of Kool-Aid powder and a little bit of water, so you'd have a very, very sweet, sugary tasting Kool-Aid. A dilute solution, on the other hand, means that the solute particles are more spread out, and you would have less solute dissolved, meaning that it would taste more watery. These terms, concentrated and dilute, are not quantitative though. When we say something is quantitative, that means that we have numbers associated with it. Concentrated and dilute are rather vague or qualitative terms. So if I told 10 people to make a dilute solution, yes, they would all be watery, but not necessarily the same degree of watery. So we have to put numbers to this. And that is where molarity comes into play. Molarity, or concentration, is a ratio. It is a ratio of the amount of solute to the solvent. But we have to make sure that our amount of solute and solvent are in specific units. When we talk about molarity, we can find the molarity, or the concentration of a solution, by taking the ratio of solute to solvent. Our solute needs to be in the unit of moles. Our solvent needs to be in liters, and we want to make sure that it's liters of total solution. So I'm going to put liters of solution here. We can kind of abbreviate or reduce this equation down, and we often see it written as capital M, representing molarity, is equal to moles over liters. This is the equation that we are going to use as we move forward and do our example problems. My first problem asks, what is the concentration of a solution that contains 1.5 moles of NaCl in 2 liters of solution? So if I'm looking for concentration, it's important to remember that concentration is measured with molarity. I like to go through and identify what each of the numbers represents, and then figure out what my unknown is. So here, I'm given moles, I'm given liters, and it's looking for concentration. Again, concentration is measured in molarity. I'm going to write the equation down. I'm going to use molarity equals moles over liters. I want to make sure that I list all of my variables out before I substitute in. This is my time where I can go back and make sure that I have the correct units before I substitute into the equation and solve. I don't know my molarity or concentration. That is the unknown variable that I'm looking for. My moles are 1.5, and I am in the unit of moles, My liters are 2.2. Now, I have made sure that I have all the correct units. I'm ready to substitute in. Instead of moles, I'm going to put 1.5, and instead of liters, I'm going to substitute in 2.2. Then, to solve for molarity, I simply divide my moles by my liters, and I end up with a concentration of 0.68. Make sure that you put a unit on that, and we're talking about concentration here, so molarity is our final unit. Now, that number means something. The higher this number is, the more concentrated or sugary our Kool-Aid solution would be. If we are looking at a lower molarity would indicate that it is a more watery or dilute solution. Our second example problem is going to be a little more complex because it is going to involve some unit conversions. So we're going to approach the problem the same way. We're going to start by identifying what each number means. My 0.8 is indicating a molarity. And now I have grams. Grams is not found anywhere in my formula, but grams is connected to the mole. If I know grams, I can get moles. If I know moles, I can get grams. Then this problem is asking me to find the liters. My equation is molarity equals moles over liters. And I'm going to list all of my variables here on the side before I substitute in. Again, I always want to do this to make sure that I have everything in the right unit prior to substitution. 0.8 is my number for molarity. I'm given 14.6 grams, and I don't know my liters. Before I substitute in, I want to check my units. Molarity is fine, but moles is not. I'm going to need to convert this using dimensional analysis to show how many moles are equivalent to that 14.6 grams. To do this, I'm going to go to the periodic table, and I'm going to add up 1 calcium and 2 chlorines. If you're not sure how to do mole conversions, please check out the link above, and in that video, I explain how to convert from grams to moles and moles to grams. So I'm going to go to the periodic table, and I'm going to add up 1 calcium and 2 chlorines. When I do that, I get 110.9 grams. Remember that the number on the periodic table that I add up is telling me how many grams are equal to 1 mole. Once I have that equivalent, I'm ready to set up my problem. 110.9 grams is equivalent to 1 mole. My grams cross off, and I get 0.13165. Now that I have everything in the right unit, I am ready to substitute in and solve. In place of my molarity, I'm going to write 0.8. In place of my moles, I'm going to write 0.13165. And my liters are the variable I'm solving for. We can either leave that as an L, or if you want to call it X, that is perfectly fine. It's our unknown. Now, if you are good with the algebra, just go ahead and solve this. But if algebra tends to be tricky for you, or you're not sure how to solve for X, since we have an equal sign here, I would suggest just putting your molarity over 1, and then you can cross multiply. So I'm going to take 0.8 times X and set that equal to 0.13165. In order to get the X by itself, I'm going to divide both sides by 0.8. When I do that, I get 0.16 as my final answer. But remember that I can't leave an answer without a unit. So the unit that I was solving for is liters. So this is going to come out in the unit of liters. This problem, again, is going to include a mole conversion as well as a milliliter to liter conversion. So there are a lot of conversions that need to take place. Let's go ahead and start setting this up. 250 milliliters is the first number I encounter. Milliliters is not in my equation, but there's a connection between milliliters and liters, so I know I can get liters from this. 0.5 represents my molarity, and that has a capital M, so I know I'm in the right unit. The end goal here is to find grams, but grams are not specifically written in my equation. There is a connection, though, between grams and moles, so I can use this value in order to determine my moles. All right, I'm going to start with my equation, and I'm going to list all of my variables over on the side. I'm going to fill in what I know, and I'm going to make sure that I identify the unit that belongs with it. So 0.5 is my molarity. My moles I do not know, and my liters are not given as liters, but instead they are given as milliliters. That means I'm going to have to do a conversion prior to putting it into my equation. There are 1,000 milliliters in 1 liter, so I can use my dimensional analysis to set this up. I have 1,000 milliliters on the bottom so that my units cancel out, and 1 liter on the top. Remember, the top and the bottom always have to be equal to each other in terms of volume. That gives me 0.25 liters. Now that I have everything in the right unit, now I'm ready to substitute in and solve. My molarity is 0.5. My moles I don't know, so I can either leave that as moles or I can call it X. And my liters are 0.25. Again, if you are struggling with the algebra, I would suggest putting this over 1, and because we have an equal sign, we can cross multiply here, meaning I can take 0.5 times 0.025 and set it equal to 1 times x. When I solve, I get x equals 0.125. Now, it's important that we always keep track of our units. If I look at x, x is going to come out of this equation in moles. Moles must go into the equation, moles will always come out of the equation. That means that this represents the number of moles. The problem is that it didn't ask me for moles, it asked me to find grams. That means that now I'm going to have to do a conversion. In order to do a conversion, I'm going to need to go to the periodic table and find the molar mass of my substance. But the formula is not written here. It's giving me the name. If you need a refresher on naming ionic formulas, check out the video that's linked above. Potassium has a +1 charge and sulfate is a polyatomic ion with a -2 charge. So when it is happy, it is K2SO4. Before you add it up on the periodic table, you need to make sure that it is stable or happy. Now that I have it stable, I'm going to add up K2SO4, and I find that when I add up 2 Ks, 1 S, and 4 Os, I get 174.26. The number I get on the periodic table represents the grams that are equivalent to 1 mole. Now that I have equal values, I'm ready to put 1 on the top and 1 on the bottom. So this time I'm going to put 1 mole on the bottom and 174.26 grams on the top so that my units of moles cancel out. I'm now going to multiply across the top, multiply across the bottom, divide my top by my bottom, and when I solve for x, I end up with 21.78. The only unit that did not cancel out in my dimensional analysis is grams. So grams, and specifically grams of K2SO4, are what my x value represents. Hopefully that helped clear up what molarity is and how we can use our molarity equation to determine the concentration of a solution. Please check out my other videos, and thanks for watching.